So, shall we?
I think if you want to get started, that's fine.
Okay. Good morning, everyone. It's my pleasure to introduce Professor Jeffrey Walling from Virginia Tech. So Jeff Walling received his bachelor's from University of South Florida and his PhD and master's from University of Washington. Before Virginia Tech, he was at the University of Utah as an associate professor. And he has held different industry positions all the way from Motorola, Intel, Qualcomm, and Skyworks. And today he's here to talk about versatile RF digital to analog converters from RF to millimeter waves to enable 6G wireless communication. Let's keep it on.
Thanks for having me. It's actually my first time at NC State, so we're almost neighbors now. At Virginia Tech's only about 3 hours away. So I'm going to start my talk with background and motivation. I'll give a bit of a tutorial on switch capacitor power amplifiers, and then we'll look at a few specific case examples of frequency reconfiguration, millimeter wave SCPAs, and then given time, I'll talk about inverse design and RF components. So people that work in the silicon industry know this chart well. This shows the 50-year history of Moore's Law and the 33 million X improvement in the number of transistors on a typical 1 inch by 1 inch silicon die over the course of that time. Over the course of that time, the transistor has been optimized to be a small low-loss switch, and it has not been optimized for its analog performance. And so we are proposing to make some architectural changes in the way that we make analog RF and mixed signal circuits. Primarily, that is that because the transistors have been optimized to be switches, we should probably try and use them as switches. So we want to use more digital circuits and fewer analog blocks or things that we might think of as amplifiers. So I generally work in the field of mixed mode transceivers, and what do we think of as what do we think is a mixed mode transceiver? Well, we're going to take the blocks that make up a traditional Cartesian transmitter that's shown here, and a Cartesian receiver that's shown here under my cursor, and we're going to replace those with direct digital to RF and direct RF to digital components. So we're essentially replacing analog heavy transceiver chains with data conversion. This gives us reduced complexity in our interfacing and signal chains, and it can be reconfigured easily if we want to operate in a multi-band or multi-standard operation. They're inherently wideband because we have high impedance interfaces everywhere except for at the antenna. So the principle here is that where possible, we're going to replace transconductors or GMs with switches and high-speed logic. Just to highlight what I mean by interfacing, in a typical transceiver chain, we have a baseband modem, a digital to analog converter, a filter, an up converter, and some amplification. And at every interface between those circuits, between the DAC and the filter, between the filter and the mixer, and between the mixer and the amplifier, there is a certain impedance condition that either of those circuits wants to see. If we make modular systems, we tend to match to 50 ohms and then connectorize the system. But even in integrated circuits, we typically have to make interfaces between individual blocks. So the person that designs the DAC is not necessarily the same person that designs the mixer. We have to know what the impedances are. And when we do these impedance translations between blocks, we inherently narrowband the system. On the other hand, a digital power amplifier is another way to implement a transmitter. And the digital power amplifier provides high impedance gate interfaces everywhere. Everything is driven by digital switching performance and none of those analog, pesky analog performance features that we talked about just a moment ago. Now, on top of this, I tend to work in power amplifiers, and what we really care about in power amplifiers is efficiency. So here is a generic CMOS power amplifier. It really just consists of a big transistor and a bandpass impedance matching network. And the efficiency of the amplifier is driven by three things: the topology. So you might have seen a class A, B, or B amplifier before, or maybe a D, E, or F. Those are switching topologies. And it's also driven by voltage or current divisions that happen because the transistor has finite output impedance. And the efficiency is also driven by loss in the bandpass matching network. So more or less, we can write that the total efficiency of an amplifier is the product of those three subdivisions in efficiency. Now, if we look at the efficiency breakdown, the losses in the matching network can be accounted for, noting that passive components have finite quality factors, and the overall network that we're trying to achieve has a quality factor, and losses are associated with a matching network have to do with the amount of impedance transformation we're doing and the quality factor of the components that we can bring to bear. From a topology perspective, this really just has to do with how we bias the transistor. If it's a linear amplifier, so the conduction angle, the topology for a class A gives us 50% efficiency. For a class B, 78.5% efficiency. AB is somewhere in between. Or we can use switching or voltage mode topologies that give us 100% efficiency, meaning that there's no power loss in the circuit, ideally. Now, the last thing that drives the efficiency is the output division. And we have current divisions if we're using the amplifier as a transconductor, in other words, as a voltage-dependent current source. And we have voltage divisions if we're using the transistor as a switch. And it turns out that it's much easier to make this last trade-off more favorable for a switching amplifier. It's easier to drive the switching resistance down than it is to drive the output resistance of the transconductor up. Again, remember that the devices have been optimized to be switches and not to be current sources. So with that, I'm going to show a switch capacitor power amplifier, which is really a mixed mode transmitter. And so what is a mixed mode transmitter? If we look at a mixed mode transmitter, we have on the left two examples of current mode digital power amplifiers. And what these essentially are banks of current cells that can be enabled or disabled by some decoder. If we turn more of the cells on, we can output more current and hence more power. If we turn more of the cells off, we can reduce the power. So we have a proportional control of the output power that's achieved by controlling quantized digital current levels. So sometimes we call these things RF DACs because of that. We have quantized states that we can kind of go between to realize a linear amplifier. Now, I'm going to primarily talk about this one here on the right, which is a voltage mode digital power amplifier. And we originally called it the switch capacitor power amplifier when we introduced it in 2011. And this is going to be really favorable for CMOS operation, as we'll see in just a minute. Beyond the DAC function that I just described, the mixed mode transmitter or digital power amplifier or RF DAC also provides mixing, so it does up conversion, and it also can provide significant output power, so it can be treated as an output stage or a power amplifier by itself. Now, if we look at the architecture of a conventional transmitter, we're going to compare that to a mixed mode transmitter. So the conventional transmitter that I showed earlier consists of our modem or baseband circuit that exists in a digital processor of some sort. And then we have a digital to analog converter, a filter, mixer, and amplification. And I've color-coded these things to correspond with where they more or less correspond in our mixed mode transmitter. All of these blocks in the figure on the left are typically analog in nature. So we're typically using the transistors as transconductors. So all blocks are really mixed signal analog. And one thing to note is our filtering generally is almost all at the analog baseband, although there is some filtering built into the modem as well. Now, in the mixed mode transmitter, we're going to rearrange some things. So most of our filtering is actually going to happen in the digital baseband. So these are digital filters. One of the nice things about this is that they're tiny compared to analog baseband filters. The mixing is actually going to be done by a logic gate. So we're going to have an enable signal that gets mixed with a clock signal and gets converted up to high frequency. Our amplification is really just a switch driver that's going to drive the bottom plate of a capacitor. So we're going to drive these signals at logic levels into the capacitor. And our digital to analog conversion happens by having banks of these essentially 1-bit mixers that are paralleled together that we can enable to increase the output power. And finally, we have some additional filtering that can be brought to bear using an RF matching network that also is small compared to an analog baseband filter because the frequency is typically significantly higher. What's important to note here is that all of the SCPA's blocks are realized using switching functions. And again, filtering is very small because it's done at either the RF or the digital baseband. We don't have any analog filtering. All right, so I wanted to talk about what makes up a switch capacitor power amplifier. And really, it is a Class D power amplifier. So here's a Class D power amplifier. The classic example was presented by Page in Proceedings of the IEEE in 1965. And this, not with CMOS transistors, bear in mind, but the classical operation was defined then. The operation here is basically a push-pull amplifier where we have a PMOS amplifier that can push current into an output node and an NMOS transistor that can pull current out of the node. And we have a filter, just a series RLC filter that selects the first harmonic and delivers it to the output. Now, the filter creates a condition that causes the voltage and current to lag one another at the transistor's drain in such a way that they don't overlap. This means that there's never current going through the transistor simultaneously when there's voltage across it. In other words, the transistor itself doesn't dissipate any power. And that's how we get 100% drain efficiency for the amplifier. Now, we note that we can make this a sliced amplifier in CMOS fairly easily. The transistors can be subdivided into smaller units, and the capacitors can be subdivided into banks of parallel capacitors. Now, when these two parallel switches are operated together synchronously, we get effectively the same Class D operation that we saw before we subdivided the capacitors. But one of the things that we can do here is we can disable one of these paths and enable another path, so we get some ability to control the output amplitude of the circuit. Now, I've shown here a simple version where we have two slices, but you can imagine we can break this down and have many tens or hundreds or thousands of parallel slices. This is fairly easy to do in CMOS, subdividing capacitors and transistors. And we can weight these things in a binary weighted fashion if we only want to have a couple of slices but have a lot of different quantization levels. Or we can weight them in a unary fashion if we want to have better matching with a lot of different quantization levels. The last thing to note here is that from the perspective of the inductor here, when we look backwards towards the capacitor and switching array, all of the capacitors always see a constant connection to a fixed voltage, in other words, a virtual ground. So all the capacitors in parallel add up to the same capacitance as they would if we hadn't done this parallel operation. In other words, the resonance doesn't shift, so we don't have to worry about detuning the circuit. All right, so let's look at the operation of a switch capacitor power amplifier. So the full voltage SCPA is shown here. We can switch between VDD and ground at the RF frequency that we desire to operate at. If we switch all of the cells between VDD and ground at the RF rate, we get a maximum voltage at the top plate of the capacitor, and the resonant circuit selects the fundamental and delivers that to the load, so we get a sinusoid at the load. But we can do this thing where we maybe ground some of the cells and switch some of the other cells at the RF rate. And here we get a charge redistribution. So when we switch the cells to VDD, so let's say we switch little n unit capacitors to VDD, At the instant that they're at VDD, the caps charge up to N times Cu times VDD. And then when we switch them back to ground, if they're big N total cells, we have a total charge that's equal to big N times the capacitance times the voltage at the top plate of the capacitor. We have to have charge conservation, so the charge in both states has to be equal. In other words, Q1 has to equal Q2. And we can solve for the voltage at the top plate of the capacitor and show that it's linearly proportional to the supply voltage and the number of capacitors that we're switching relative to the total number of capacitors in the array. So we have what amounts to a linear amplifier now, using only switching circuits. Now, it's a quantized linear amplifier in the sense that the steps that we have here are quantized, but nonetheless, we have a linear transfer characteristic. This is a very linear transfer characteristic because we can we're limited really just by the matching available in the circuit, and that is done in typically a CMOS technology where we have very good control of matching between transistors and switches. And we're going to model this as a voltage variable switch. So here's our model of the SCPA. We have a Thevenin equivalent circuit. And for the circuit on the left here, we model the switching behavior as going between VDD, a scaled version of VDD and ground at the RF rate. And we have the total capacitance in the array and the inductance in series. And we can calculate the output voltage on the resistor as being 1/2 4 over pi little n over big N times VDD. So again, a linear amplifier. The 1/2 and 4 pi come from RMS operation and selecting the fundamental component of the Fourier series expansion of the square wave. Now, if we want to calculate the input power, we look at things a little bit differently. So instead of that voltage variable switch, we have a switch that's going between VDD and ground. And then we have the total number of capacitors that are being switched in series, and we have in shunt the total number of capacitors that are not being switched. If we do the switching operation very quickly, we can't change the current through the inductor instantaneously, and that means that we can model it like it's a current source, or we can open circuit it, disconnect it from the circuit. And all that we're left with is the series combination of the capacitors that are being switched in series with the capacitors that are not being switched. We're switching these things, so we have C VDD squared F power that's shown here. And we can see that the power is minimum when we aren't switching any of the capacitors. In other words, little n is equal to 0, and it's also minimum when we're switching all of the capacitors. In other words, we have a purely resonant circuit. It reaches a maximum for a middle code. Little n is equal to big N divided by 2. The subscripts are actually mixed up here, or the numerator should be big N minus little n. Just notice that. All right, so let's ask about total efficiency in the system. So we just looked at really what we would call the drain efficiency of the system, but we have other things to consider. We have lossy inductors. These cause losses associated with the matching network. So that's this alpha factor that I show right here. We have switch parasitic resistance. This is the voltage division shown as the beta factor down here under my cursor. And then we have to drive a bunch of different logic cells and switching cells and things like that. So we have parasitic CVD squared times F power consumption. But what's nice to note about this power consumption is that it benefits from CMOS scaling because generally, as we scale from one technology node to another technology node, the capacitance and voltage supplies decrease, albeit nowadays in the area and really fine line CMOS technology, the voltage and capacitance scaling are not happening at quite the rate that they used to. We can look at an efficiency characteristic showing the drain efficiency, which was the efficiency that we would have found from the prior slide, and the realistic system efficiency that's calculated here. Now, one thing that's important to note is if we were to compare this with a linear amplifier, the efficiency characteristic versus backoff power for a linear amplifier rolls off more quadratically, and so we have a big efficiency advantage in what we call output power backoff compared to linear amplifiers. So how do we design one of these things? Well, we start with a full power amplifier. We assume that we have an operation power that we want. We calculate the power as a function of the width and length, the width of the NMOS and PMOS devices. We ask if we meet the spec. If we don't, we reduce our optimum termination resistance until we do. And then we choose the width of the PMOS and NMOS devices such that we achieve a maximum power added efficiency. Now, what's really happening here is we have input power that's proportional to the width of the devices. This is CVDD squared F. So as the capacitance increases, the input power increases. And we have power that's proportional to, that's inversely proportional, proportional to the switch's resistance, which is inversely proportional to width. So what you see generally is that we have a convex optimum versus the width of the periphery of the device, where our efficiency peaks and we're still able to deliver the desired output power in our system. So this is really an algorithmic design. If we have models that tell us how much switching resistance and capacitance we get for a given width over length ratio of our devices, we can plug this into an algorithm, run it, and it'll tell us how big the switch needs to be. Now, beyond that, we might need to subdivide it into multiple slices, and that depends upon how linear our amplifier needs to be, and what level of quantization noise is acceptable in our device, and what the matching capability of our individual process is capable of. And we detail this in some of our journal papers, for instance, in the MTT paper shown here. Now, one thing that I really want to highlight about these RF DAC designs is that it's really a slice-based design. So we have an amplifier that consists of an array of capacitors and switches. One slice of that array is shown here. In this case, we're using a Cascode switch in order to be able to use a slightly higher output voltage. This helps us to deliver more output power to the load. But the slice itself just consists of switching circuits. So we have some clock driver, some logic gate, and some buffering in order to drive the switching up to logic levels while driving relatively big capacitances. These switches might be fairly large if we want to deliver a lot of power. Everything, though, is optimizing the timing in that slice. It's not really focused on optimizing transconductors or things like that. And generally, we can optimize one slice and we can tile it up to the desired resolution. And we don't have any analog or RF interfaces until we get to the top plate of the capacitor. All right, so knowing that, let's look at some specific examples. So first, I'm going to talk about a frequency reconfiguration, SCPA. So this slide shows the US spectrum allocation and where our communication bands lie for 5G are really all in this extremely crowded spectrum down in the bottom of the figure. Now, if we look at this, at each of these horizontal lines, this is more or less a decade of frequency. And when we subdivide these things, it's different applications that have to exist in that span of frequency. And you can see a lot of different services in this 5G spectrum that are being used, and they all have to coexist together, and that's very challenging. Now, in 6G, there's speculation that 5G. How many people know that 5G used millimeter wave or uses millimeter wave? It ostensibly uses it, but unless you're on Verizon in some certain urban areas, you probably are not using any millimeter wave 5G or have a very expensive iPhone as well. So millimeter wave frequencies are up here. It's speculated that in 6G, they're going to actually roll back and start using centimeter wave frequencies and what they're calling FR3 that exists between 7 gigahertz and 24 gigahertz. Propagates a bit better than millimeter wave frequencies, has better latency, but also gives you some more bandwidth as compared to the sub 6 gigahertz frequencies that are commonly used in 4G. Now, knowing that we have all this congested spectrum, we want to have, and we need to be able to operate really across a lot of this, maybe contiguously. We need flexibility in our transceiver design for more efficient use of the spectrum. In terms of transmitters, there are a couple of different approaches to making flexible transmitters. So one way is to make an extremely broadband transmitter using something called a distributed power amplifier. And really what this thing is trying to do is mimic a transmission line with some active devices in the middle of it in order to drive a lot of power across the wideband frequency. It has wide instantaneous bandwidth, but there's a lot of additional loss. There's insertion loss in this artificial transmission line. We have all these devices that have to be biased for linear operation. And we have a couple of couplers as well that have to be broadband, and generally they tend to be pretty lossy in order to make that happen. We could also do multiple narrowband power amplifiers, and this is more or less what's actually done. Now, if you were to open up the RF front end chip on your cell phone, you'd probably see a bunch of different spiral inductors representing a transmitter that's operating at slightly different frequencies or tuned to slightly different frequencies. They're multi-band transmitters. So you have a narrowband power amplifier and some filter. There's also generally a GaAs or a GaN front-end module where the filtering is done as well. This gives us better peak output efficiency and power amplification, but it doesn't allow for any design reuse. You have to design several different tuned circuits, which increases time to market. And it also results in larger die area because I need to have different bands covered, different filters, different things like that, which adds cost. One last thing we might try is to make a single wideband power amplifier and then isolate it between different filtering networks. This gives us only one power amplifier, but it does give us a trade-off where we need some type of isolator, which is generally a magnetic component, although nowadays it can be what's called an in-path component. If we can get one that handles power well enough. And we're essentially in this one trading off peak output power and power added efficiency for bandwidth. So we wanted to look at something slightly different. So we proposed to use a tunable narrowband circuit. Now, you're almost never operating when you're operating in a cellular system across wide swaths of frequency instantaneously. In fact, we channelize the operation, so you're typically only operating in chunks of 40 megahertz to 100 megahertz, something like that, at a given time. So we noted that we have a capacitor array with our switch capacitor circuit, and we could add a capacitor in series with the capacitor array that doesn't change the function of the capacitor array in terms of how it provides linearity, but does give us a degree of freedom in controlling the total amount of capacitance that our resonant circuit sees. And this allows us to tune the frequency. So the total capacitance that this inductor sees is now going to be the series combination of all the capacitance in the array with some digitally programmable capacitor. And these digitally programmable capacitors can be realized using MIMS or 3.5 processes. Or fundamentally, they can also be implemented in back into the line metallization, or we could even try using MOS varactors and things like that if we were doing it at slightly lower power. So how do we do this tunable SCPA design? So we're going to calculate R opt from supply voltage in order to from our supply voltage and our power output requirement. So we have a power output requirement. We have an equation that tells us what the optimum termination needs to be. Here we've plotted the efficiency of the SCPA that we're just looking at as a function of the total efficiency as a function of the SCPA efficiency and the matching network efficiency. And we see that we get peak efficiency for a network quality factor that's somewhere between 3 and say 8, depending upon the output power level that we're trying to operate at. So the difference between in these curves is here we're trying to operate at a 3 dB back off, and here we're trying to operate at 6 dB back off. But more or less the efficiency range that we want to operate in is the same that we wanted to operate in before. Once we know what our network quality factor is, we can go and calculate the total capacitance, and then we can calculate the resonance, the inductance that we need to resonate with that capacitance. So what we've done for a tunable SCPA architecture is we have our SCPA, we have a tunable capacitor array, and we have some digital frequency control that controls that tunable capacitor array. Now, in our case, the capacitor is a 6-bit Qorvo digital programmable capacitor that's available in a standard SMD package. And then we provide a broadband matching network at the output in order to transform the resistance to a level that allows us to deliver power. Yes.
You fixed the inductor, but you said you wanted it to work over really wide frequency, but you just showed us like there's some optimum inductor, so there's right there.
Yeah, there's a bit of a trade. Really, all we're doing is showing you that we want to operate with some optimum quality factor, so that's going to dictate the size of the inductor, the relative size of the inductor. We don't get everything for free, so if we could program the inductor also, it'd be a bit more optimal, but we don't have programmable inductors. But I'm going to show you nearly 60% fractional bandwidth for a digital power amplifier in just a moment. All right, so this is the circuit implementation. So what I talked about before, we have a bunch of slices that look pretty much identical to what I showed you earlier. We have a capacitor, we have a switch driver, and then we have some logic that selects individual slices to be switched or not to be switched. In our case, we divided this into a 4-bit unary array and a 4-bit binary array. And this is basically just a trade-off between having a lot of parallel slices if we do a unary array and having better matching if we do a unary array compared to fewer slices with worse matching if we do binary. Our total capacitance was 1.4 picofarads, and we can tune it between 0.37 and 1.37 picofarads using the digital capacitor array. The Q of the digital capacitor is between about 8 and 42, depending upon the state that we're operating in. And the Q of the inductor, we used an off-chip passive, was about 50. So instead of having a narrow band matching circuit, we used a fairly broadband bail-in in order to give us an impedance transformation that we need in order to deliver high power. So this is a die photo of the chip. It was done in 65 nanometer CMOS. You can see the cap array and switches right under my cursor. And then we have all the logic drivers, decoders, and timing and clock buffering and things like that. Also, we spend quite a bit of time optimizing the supply and decoupling network to make sure that the voltage as it moves inward from the periphery of the chip stays relatively constant at each switch. This is important to get linear operation. We did a chip on board circuit. So the chip is more or less under my cursor right here, and the DPCs are below the cursor right here. And we do a connectorized measurement where none of the losses are de-embedded. So the measurements that we're going to look at in just a moment don't include any losses out to the connector, whereas a lot of comparisons, they wafer probe circuits. So this is the measurement results. We have output power, peak output power of about 21 dBm, relatively flat across the band. The variation is actually caused by the LC bail-in. It could be corrected with a bit better design of the LC bail-in, or maybe a different topology like a Guanella bail-in that's popularly used nowadays. We get a frequency response from 1.4 to 2.5 gigahertz. This is not showing every step in frequency that we can do, just showing representative steps. And we cover about 60% fractional bandwidth. If we look at the system efficiency, as you might guess, it peaks at lower frequencies. We still have CVDD squared F losses. So as the F scales, the efficiency tends to go down a bit. But nonetheless, the system efficiency is from 25 to about 40%. And remember that this is the total wall plug efficiency. So this is really the output power divided by everything that's going onto the board, and without losses de-embedded. When we measure our linearity, these are DACs, they're not amplifiers. So most amplifiers we look at and we characterize the AM to AM or amplitude modulated curve, and the AM to PM or amplitude modulated to phase modulation characteristic. But for our DACs, we actually measure the INL and DNL. We can more or less think of the DNL as the gain of the DAC. And one of the things that you'll notice is that these amplifiers don't saturate. The INL and DNL stay pretty constant across the range of operation, whereas most linear amplifiers are going to saturate at some point. Ours work all the way up to the maximum code, and then they stop when we can't iterate the code anymore. We can't deliver any more power, so they don't saturate. They just stop increasing. So we measured this with some, at the time, 4G-like signals. So these are LTE, 64 QAM, 20 megahertz OFDM symbols with a data rate of about 100.8 megabits per second. Without any DPD, we're able to get EVMs of less than 3.9% RMS. And here you can see the PSD as we tune across the range of operation with those modulated signals. The output power average is about 14 dBm, and the system efficiency average is about 15.7% across the range of operation. Again, loss is not de-embedded. One of the nice things that you can see about the tunable narrowband operation is that the out-of-band noise typically in a digital power amplifier is dominated by quantization because this is fundamentally a DAC. So quantization noise is white. But here you can see that the filtering, the narrowband filtering is actually helping to shape and reduce the quantization a bit. This is just a comparison of some prior wideband architectures that we looked at before. You can see that ours is pretty favorable in terms of all the metrics, in particular, especially because we did not de-embed losses, whereas most of the other ones were looking at wafer probe measurements. All right, so the next thing we wanted to look at is how do we operate these things at higher frequencies? So the one I just showed you was more or less operating in S-band up to 2.5 gigahertz, but we wanted to go higher in frequency. And so the original SCPA has a limitation, has two primary limitations in increasing its frequency. The first is that PMOS transistors are low, and our architecture uses both PMOS transistors and NMOS transistors. We have to switch to the high side supply and the low side supply, which means we need a PMOS. Most power amplifiers only use NMOS transistors, so that's a downside for us. The other thing is that parasitics have to be charged and discharged every cycle. More or less the two parasitic capacitors that are shown in gray on this slide, they get charged up every cycle, and then the charge gets dumped to ground, doesn't get sent to the output. So that's waste. It shows up as inefficiency. We're going to solve the first problem. We aren't necessarily going to solve the second problem, although we do solve it a little bit because we can get some favorable trade-offs in the size of our devices. So if we want to operate at high frequency, we can note that we can subdivide that inverter into 4 parallel slices, and this makes what we would commonly know as an XOR gate. And if we were to drive the XOR gate with clock signals that are in quadrature with one another, then we would create an output waveform that had twice the input frequency as the input waveform. So we get frequency multiplication, and we get this for free just using essentially multi-phase circuits and parallelization of the transistor. Now you might ask, well, if I wanted to do a multiplication, why wouldn't I just take the harmonic content that's generated by the switching operation in the first case and just retune my LC filter so that it selected the third harmonic, say. And there's a very good reason for that, and that is that the third harmonic content of that waveform is still about 9.5 dBs down compared to the fundamental component. So we're throwing away a lot of power, and we don't have a lot of power to waste typically. Well, we can generalize the frequency multiplication. So here's the general case. We have M parallel branches. And more or less what happens is that during each cycle, a pull-up branch closes, then a pull-down branch closes, then a pull-up branch closes, and we go through M cycles and get a multiplication where our input frequency is a factor of M less than our output frequency. And we decided to build this and test it out. So here's a circuit that we did. It was just a tripling edge combining Class D power amplifier. And we have a 3-branch XOR gate where we tried to share 1 branch. I'm going to tell you don't do this. Just go ahead and add the redundant transistor. It makes things more linear, but the tripling operation still does indeed work when we do this. We wanted to compact the cell for a millimeter wave circuit that I'll show you in just a moment. And I'll still say don't do that. So this is a 65 nanometer prototype. The drivers and switches are to the left and right of the output matching network. And there's multi-phase clock generation and distribution on the chip from a single clock receiver. It achieves operation at 4.5 gigahertz with a 1.5 gigahertz input signal. And output power of about 22 dBm, system efficiency of about 30%. And we did not add any capability to do linear amplification with this one. So this is just a non-constant, this is a constant envelope modulation, BPSK. And we get pretty good EVM and ACLR performance. We compare this to some other work in the same space, and we have pretty favorable numbers, again, considering that we're getting a 4.5 gigahertz output, but only switching at 1.5 gigahertz at the input. So how do we extend this to millimeter wave? Well, to extend to millimeter wave, we have the following circuit implementation. We wanted to operate at around 30 gigahertz. There's a popular 5G band that starts at about 24 gigahertz. And so we wanted to try and cover some of that. We did not think that we would be able to use polar operation because polar operation is fairly wideband. Polar operation is where we encode the amplitude modulation and phase modulation. Here we're going to encode in phase and quadrature or Cartesian modulation into our circuit. Now, at first we decided, well, we're going to try and just triple the frequency at the output stage. But we discovered that distributing 9 gigahertz multi-phase signals across a fairly big chip periphery consumes a lot of power. In fact, it consumed almost as much power as we were saving. So there was really no advantage. And so what we decided to do was to generate all the frequency that we needed locally in slice from a single common 3 gigahertz multi-phase reference that we distribute just to the input of each of these slices. So each of the slices here is more or less similar to the slice-based concept that we showed you earlier, albeit we're doing some local frequency generation in every slice as well, in addition to the logic operation and driving operation that I showed you before. So we take 3 gigahertz and we have a local DLL that triples to 9 gigahertz. And then we have our mixing and edge combining operation that then multiplies the signal to 9 gigahertz. And then we have in phase and quadrature components that we sum together using a Cartesian combiner. At the top plate of the capacitor array, we have our quadrature analog signals that are driving into that combiner. Now, just to talk a little bit more about how we do the in-slice design, every slice has a DLL, and the DLL is matrix locked to every other slice. So you can see that the DLL has injection that can be controlled by these coupling resistors in order to get optimal injection performance in the DLL. This is a fairly unique design. We wanted to make sure that all the cells were synchronous. And so by injection locking all the cells to one another, we maintain synchronicity and also have low power. The slice design is pretty similar to what I showed you before. The difference is that we have 3 phases of clock that we have to put into every slice. So we just have basically triple the number of logic and buffers. And our output switch design is similar to what I showed you before. We were operating at millimeter wave, so we wanted to compact everything. And that's why we tried to do this Euler path where we showed that we could reduce one transistor, compact the design just a little bit. As I mentioned, this results in an odd beat frequency every 3 cycles because it's very difficult to balance the resistance of this single PMOS transistor and single NMOS transistor. It would have been much better to just have fully parallel paths and suffer the area penalty. This is the SCPA layout. Now, this is now a millimeter wave circuit, and we had to consider transmission line like effects. So when we originally did this, we had one linear array, and the wavelength of that linear array was on the order of lambda by 4, lambda by 6, something like that. And so you can imagine that we get voltage maximum and minima as we go across the cap array. And it's very difficult to make a linear amplifier when you have a transmission line effect causing these local voltage minima and maxima. So we decided to subdivide the array into 4 parallel arrays, and we kept the length of the transmission lines to be more or less than lambda by 10 to minimize those transmission line effects. And then we have a common tap point where we sum all of the amplifiers into this tap, and then the transmission line effect doesn't matter as we propagate it to the output. This is the Cartesian combiner. It's an isolating combiner, which is made of a 2-way stacked overlay transformer. And in order to reduce the parasitics in the cap cell, we spent a lot of time engineering a custom AP-MOM cap that you can see there.
I think I missed, why are you using IQ combining here and not earlier?
In this case, we were trying to use really wideband signals, and with polar modulation, you have to do a conversion from Cartesian to polar that ends up with really wideband signals. We normally need something like 10x the bandwidth. We're trying to do 400 megahertz signals, so it would have implied that we need 4 gigahertz bandwidth in our amplitude path and phase path. Yeah. So here is the measurement setup in the dye photo. You can see the partitions in the cap array shown here. One of the nice things about working at millimeter wave is that the power combiner is actually smaller than all the other circuitry. We did a chip on board assembly for all the I/O. We did wafer probe the output in this particular case. So we get 21 dBm out at about 28 gigahertz. Peak drain efficiency is 37%. And we break down all the way down to system efficiency. So you can see the drain efficiency, and then where we're losing our efficiency in the drivers, LO buffers, and such. Our system efficiency is about 22%, which is pretty good. I'll tell you why in a moment. And then our linearity is shown here. So here we're measuring that linearity characteristic and showing you our INL and DNL. The DNL is less than plus or minus a half LSB for a 6-bit DAC that's operating at nearly 30 gigahertz. And this is enough to do modulated measurements. So here we do a single carrier modulated measurement where we get an EVM of 3.3% for a 2.4 gigabit per second signal, with an ACLR of about 30.8 dBm. This is not using any digital pre-distortion, so this is just a purely linear amplification measurement. Now, I forgot to include our comparison table, but I'll highlight most of the comparison that we look at compares this to a linear amplifier. We compare very favorably to a linear amplifier because we also have data conversion and frequency up conversion in our circuit. Whereas most of the comparison is just to an amplifier, maybe an amplifier plus a mixer.
You said there was a beat tone. Where does that beat tone?
We don't show the wideband, wide out of band measurement, but it happens at the third harmonic, so it'd be at like 90 gigahertz, which we didn't have capability to measure. But we could see it in simulation. Yes.
Yeah, so these sensors also with the paths de-embedded or everything?
No, this is wafer probe. Yeah. Most of the literature also compares their wafer probe measurements, so it's still a fair comparison. All right, so just quickly, in the last couple of minutes, I'm going to talk about some other work that we're doing right now in inverse design. So if we look at photonic integrated circuits, there's been an interest in doing these randomized pixelated surfaces for operation as things like couplers or polarization splitters, diplexers, things like that. What they showed is that you could take classical electromagnetic designs of these components and then randomly allow transformations in the structure. And some of the random surfaces would perform better than the traditional structures. But there's no classical design that tells you how to make this thing. So literally, they just transform artwork, run an EM simulation, and determine if it works better or not. And so you get these wild-looking designs where they indeed are more optimal or proven to be more optimal than the classic design. So we decided to start looking at pixelated RF components, and there have been a number of examples recently. So, for instance, from Professor Sengupta at Princeton, they have a pixelated RF matching network that they showed here that achieves really wideband performance in terms of its small signal parameters. It does have a few problems in that they're providing the DC bias through this network as well, and there are a couple of places where they have maybe a single pixel width worth of metal to provide all the current for their amplifier. This was shown at IMS last year. It's a pixelated antenna, but interestingly, we can do the same types of things with pixelated surfaces for just RF regular RF components. So we're using inverse design in order to design these things, and in particular, what that means is we start with a specification for a frequency response that we want, and then we set that as an objective function that can be optimized, and we can do multiple objectives at the same time. So, for instance, we can have an objective to optimize one band and another band. We can optimize return loss and insertion loss, things like that. And we can either start from a random design or start from some initial starting point. We presented this at Newcast last year. This is a direct binary search. Basically, what this does is we start with an initial pixel map, a figure of merit calculation based upon, say, desired S21 performance. And then we randomly flip pixels and just ask, did the design get better or worse? If it got worse, then we throw away the change and try another one. If it got better, we keep the change and try another one. And just check to see if we reached an iteration limit. We built a suite of tools called Pixelated RF. It's on GitHub, where basically we do everything with the pixel map operation. So we have we create a CSV file. The CSV file is just ones and zeros. A 1 represents put metal there. A 0 represents don't put metal there. And then we can export our artwork into commercial EM solvers like EMX or ADS and run a simulation. So we've done all types of multi-port simulations. Our tools can generally handle from 1 to 6 ports, and they can place the ports on different sides as well. So we can make fairly complicated structures. One of the things that we had to worry about actually is when we draw these pixelated surfaces, we tend to draw them as having a perfect etch. In other words, in the perfect etch case, if I have 2 diagonal pixels, there's no electrical contact in the corners. And if we're using 2.5D or 2D EM simulators, that means that no current can flow through those paths. However, when we build these things, they tend to either under etch, in other words, they don't completely break the connection between pixels, or they over etch, they do completely break the connection between the pixels. Our tools are actually able to estimate either type of design. It really depends upon how you're having the thing manufactured, whether you're going to do an actual etch or whether you're doing a milling process or things like that. So here's an example of a dual band filter that we designed. You can see the initial seed that we started with. This was generated completely randomly. Our tools can allow for symmetric versus asymmetric generation of pixels. So here you can see a clear line of symmetry along the y-axis. And this is the final design after iteration. We had a goal to basically make a DC to S-band filter and then a uniband filter. The optimization here staggered at about 121 iterations. And we built a filter just to show what we could do. So here's the experiment. This is maybe the cheapest experiment I've ever done. It was a copper-cladded FR4 that was milled on a cheap milling machine. So just one of the lab grade tools. Probably cost $3 total. So here you can see we get pretty good agreement between our de-embedded measurement and the simulation results showing what's possible. Again, we're trying to do a filter that goes from DC to S-band and then covers the uniband as well. With that, I will go ahead and stop and take any questions that you have.
Cool.
Any questions? For this inverse design approach, what's the right metric that we should be using for optimization? So how do you choose the metric or the objective function?
There's a lot of literature on choosing the objective function. In our case, originally we were actually choosing objective functions that were just linear combinations of several different parameters that we were looking at. But you tend to, if you do that, you tend to get overfitting to one objective. For instance, return loss tends to get rewarded very heavily. And so you start seeing things like the function will be driven down to minus 60 dBs when it doesn't really matter. So you have to be careful with how you choose those, but there's a lot of literature on how to choose that. And we just follow that. We're not making any innovation.
Related to the same kind of part of the presentation with the passives where you're in the pixelated stuff, how would you pick the mesh size, for instance, of the pixels in the overall grid?
So in our case, the pixels are roughly a 30th of a wavelength. And we typically mesh at, well, it depends on the accuracy we're going for, but we typically mesh with either a 20th of a wavelength or a 30th of a wavelength. And that just tells you that you're going to get one mesh in there. Now, we're looking for interactions between pixels as well on the edge. So we tend to also edge mesh, which means every pixel gets about 5 cells in it, in most of our simulation.
Regarding the switch cap PAs, you did mention that it gets better with CMOS scaling, mainly because you have lower the switch resistance and capacitance overall, it just goes down. From a switch perspective, going lower to a lower technology would probably enable you to go to higher frequency. Like if you just look at the switch alone.
Yeah, if you look at the transition, so the earlier stuff was done in 65 nanometer and the later stuff is done in 22. Now, fundamentally, actually, we probably could have done some of this stuff. We don't need to go to 22 to get 30 gigahertz performance. But there's one thing I didn't really talk about, and that is the digital filtering that we do. That stuff tends to operate at much lower power in scaled CMOS. So all of our digital stuff works way better in scaled CMOS as well.
If we, for example, take something like another technology, the metal stack that probably has a lot of, it's very lossy, and it's got a lot of resistance and it's extremely lossy. So do we have to compensate for that through switch design? or do we just need to add more slices in order to?
So my student Ali, who's actually at Intel now, he did a tape out at Intel in their, I believe it was 22 nanometer fins. And one of the things that we noticed was that our combination that we did tend to favor smaller structures and more power combination, where we could make power combination out of overlay transformers that we could compact quite a bit. So yeah, there's a lot of work that's done in minimizing the loss in the network, and that really is making good practices, making wider metal strips, stacking metal where you need to, and then trying to not have too many crossovers. That's actually where a lot of the loss ends up happening.
I have one question.
Mhm.
Your tunable SCPA. So your ACPR measurement super good. Is that because individual slices are linear? But still you're switching, right? Your intermodulation products will still come out.
Yeah, I mean, you can see some of those.
But is there an intuitive way to understand why the ACPR is even better than a linear amplifier?
So there are two things. So one, we don't have any compression in our amplifiers. The amplifier, when we most amplifiers, you increase the input power, and at some point the characteristic curve saturates. Ours doesn't saturate. We just reach a peak and we can't increase power anymore. Now, where the nonlinearity does come in a switch capacitor power amplifier is from the supply network. If we have any distortion that's introduced from the supply network, meaning we have a significant amount of current that's going through bond wire inductors, so we have LDIDT to worry about. That LDIDT can show up as a compression like behavior, or as a compressive like behavior, and it can also create memory effects. So the big thing that we do is spend a lot of time making sure that the impedance of the supply network is as flat as possible, and that mitigates the problems. But really, we don't have a fundamental reason for nonlinearity. The nonlinearity all comes from second order effects like bond wire inductance.
Further questions?
You are using an array of capacitors for this configuring for different frequencies, but there has also been like some work, not in like this circuits, but like in antennas, for metasurface antennas, they are using this Vector diodes to configure the resonant frequency. So what's the comparison between using an array of capacitors versus like using something like a Vector diode with different DC bias to give the frequency?
Well, these are fundamentally different operations. So one, you're talking about tuning a resonance of some sort, whereas in our case, we're talking about controlling a charge sharing. So I don't know that there's really any comparison, any direct comparison to doing that. Now, theoretically, we could probably come up with some way to do linear amplification by, there'd be some mechanism where we could switch a diode array. But I haven't spent a lot of time thinking about that. I'd have to think about it a bit more. Yeah.
So with that, let's just
Yeah.
Yeah. I mean, one thing is that just battery bank. Ideally, I'm getting or shortly to the 3 minute side, depending on and in terms of
at any time relevant to your interest or any time that a talk is aligned with your interest? Yes, sometimes. Yeah, there's was a talk, like that there's or weeks ago about more sensing. Okay, yeah, that was aligned. That was closely related. That was the.
So you have like a person or not, also be very, sort of fundamental operations. It's a. Yeah. Yeah. Okay, yeah.
It's an important message, for sure. It's something that we've talked a lot about actually, because sort of, two viewpoints to it. One is that the topics are specialized. So like you said, there's a difficulty in connecting with that topic, difficulty with connecting with the presentation. Sometimes you can feel like efficient. I think the flip side where we sort of came at it thinking about how to organize this was that we also want to make sure that students, especially new students, are kind of aware of the different parts of PC in the different research areas, as well as interacting with students that are from other areas. Right? You may be in the cloud, you sort of get silos in your area, right? Without the other aspect I think is kind of different. That we try to find the speaker. That's important to the presentation, but at least a whole semester you get the whole thing. And then we always tell the speakers, well, keep in mind the audience is broad, right?
Yeah.
So I think they have that message going into it. I think speakers don't do it all. As they don't, get broad at all. Others start broad and get very big, and others stay a little bit fine. I think as a result of each speaker, I think it's different.
Yeah.
Different experience, maybe you can call it.
Yeah, I know it's a difficult problem for you guys.
Sure. Sure.
Yeah.
I mean, I guess what I'm trying to harvest from the conversation is a suggestion that we should get speakers, or is a suggestion that the students should have more say or input into the speakers, or how would you tackle it?
I would say just push the speakers to be more, like the talk should be more broad. Yeah, because everyone is ignorant in different subjects. So in this subject, I'm totally ignorant, so I'm not sure I can understand so specific talk. But if it was broad, it can make sense.
Yeah.
So I think
So change the ratio a little bit.
it comes to the speak of how you can deliver the message.
Okay, yeah, that's fair. Yeah, I mean, I think, I know that every speaker wants to get into the details of what they're working on so they can kind of show off, but I think that you're right. Keep the ratio a little bit more.
Yeah, there is always like appendix,
Yeah, okay. No, thank you. I'll definitely keep that in mind. I think to be perfectly transparent with you, the tricky thing that exists once you try to tackle that in practice is, from our perspective, those that would be either. Same sort of thing. Maybe my definition, what a broad definition is, someone else's definition, you know what I mean? So then, do I get into, show me a presentation, I want to edit this.
No, I mean, it's not like.
So I think that's the tricky part, but your point is well taken.
Okay.
Yeah, well, thank you for letting me know.
Thank you
If
so much.
you have other ideas or other questions or comments, feel free to let me know. I mean, I'll take this to Michael, Danielle, and Dr. Alwad as well. We'll definitely talk about it as a group.
Thank you so much. Thank you.
Thanks. Hey, how's it going?
Great.
Yeah, I wanted to tell you, I have to move that meeting because
Yeah.
I'm giving a presentation at that time. So I have to look at my calendar. I don't know whether you have a particular time that you consider.
So when you have all of those.
Okay. I think you sent me your time, so I'll look at it. Yeah, I'll have to, well, let me see if we can do it right now, because I've got some classes, so we can probably do it.
Eventually a problem.
There was another guy from.
We have we're making the. The search guy. And the other thing to think about is that it's not one point filter, it's like parallel.
Tuesday afternoon, you said works, right?
No, and when it,
I mean,
actual,
coming out again.
Yeah, so this guy I talked over this program and he was like, yeah, you should hear this year's YFA.
I have a plan to 3 o'clock, so
On these topics are all.
yeah, you can start right at 3. Yeah, what time is your class start?
Okay, I don't just care about.
For a while.
For a while.
You know,
They're really the trick.
But he said most of the times, I mean, somewhere.
So that I know I have to push myself to run back early, I'll try to get.
No, let's
And
do
then-
2:15 to 3 o'clock.
Actually, hold up, where is your class?
EB2.
Oh, perfect, okay, then let's meet at 2, because my meeting is in EB2.
Oh, okay.
From 2 to 1 to 2. So
Okay.
1 and 2, and then, can you, I don't know if you could do that, okay. If I haven't updated it by Monday, remind me, what I'll do is I'll go into the calendar invite and see if I can just book a meeting room.
Okay,
For an EB2, and then we can just see it over there.
that was,
Okay, perfect, we'll do that then. Sounds good, cool. You have everything you need for the mask order?
no, yeah, I went today morning into the lab to like make sure it's the same orientation and stuff.
Yeah.
So now I'm just, I got the content, like, I had a class today morning, so I couldn't.
Okay.
Maybe.
That's fine, I just want to double check, okay.
No, I think it's all set.
Okay, tolerance and everything is good, 'cause I didn't look at the quote that they sent.
Tolerance is 25, 0.025 microns, so I think
the way
it
it
was
was
pretty good over there. I have a question, doing the DC purchasing stuff
We should, we
in
said.
that website.
Yeah,
And
And
should I like upload the invoice or the?
Yes, yeah, there is a box there that-
quotation?
Oh, no, invoice, you shouldn't have an invoice, because the invoice comes after the job is done. So
Yeah,
you'll put the quotation that you got from the.
so the quotation also works, or if I wait for the invoice and then upload the invoice to that system.
No, so this is a request to place an order, basically. So what will, so basically, before you could ask the vendor to do anything for you, the university has to make sure that you have the money, basically, to do the work.
Okay.
So, what could happen is that, and you could ask the vendor how they would do this, but probably it's a new thing will happen in parallel. You will send them the files, as files, and then probably in that email, I would just say.
This is 22 SES,
Our department to kind of reach out to you, so that give them a heads up of that payment side. when you take
Okay.
it That way, and then you submit the purchase request.
Uh-huh.
They don't have much,
But I need some kind of.
Okay, yeah.
Come from, and then once all that is cleared, then something like CE is supposed to call the company
Okay,
and say, here's the payment information.
okay.
So, you
So
might have to.
this has to be approved and like set before even like we, or,
Yeah, they won't start the job until the
They get
EC
the-
guys,
okay.
yeah, usually.
okay,
Sometimes it doesn't work that way, but usually that's the way it works.
okay.
So, this is a little bit,
But,
I don't wanna say atypical exactly, but you can imagine the way it works, like we order something from Amazon or whatever, blah. It's like you place the purchase request, you don't deal with Amazon directly anyway, and the purchaser from the
By the way, I'm
department
not a-
buys it for you, then you get it.
Okay.
In this situation, it's a service, so you're gonna get something after, and the service relies on technical, the purchase, the EC department.
Okay.
So you may wanna put a little note inside, the purchase request, there's a box there, and just say something like, I am submitting certain type of information. You can even maybe look, there's a way to put an email copy of what you're sending them or something.
Okay.
Just do something like that so that the department knows kind of how to like find that.
Yeah, I was following your instructions on the PO stuff, so I was like, I don't have an invoice, but I have a quotation, so.
Oh, did I use the word invoice?
Yes.
Oh, okay, maybe I just, that's what the design word they call it, yeah.
Okay.
It's an estimate, not the estimate or a quote or.
Yeah,
whatever.
that works, I'll finish up the paperwork today.
Okay, perfect, sounds good, cool, thank you. Yeah.
Yeah. Well, it's, I mean, that's a.
The old style. From what I understand, still you can go through the back end. Do a few months on there and maybe they ask for work on it, but they're still gonna feel the water, some of those will actually. Because those you wouldn't share market, they would just be like. A bitch. In that case, I don't know when it got rid of. So anyways, this should begin with.